Hello, this is Ben. I'm group 12 of the AI class, and I'm going to go ahead and run you through the experiments that we conducted on our final project. What we did was procured a data set from Kaggle that predicts heart disease from the following criteria: age, gender, chest pain, ECGs, max heart rates, things like that. I believe my group mates will talk a little bit more about procuring that data. I'll run you through what we have here. So first, we're going to use data frames. We're going to make some plots. We're going to use SciPy and NumPy just a little bit. I'm not sure that we have a lot of Seaborn in here, but those are the required libraries. We import our comma-separated data set as a data frame, as a pandas data frame. And the result is this. Everything gets renamed to things that make more sense to us. For example, rest BPS actually ends up being resting beats per minute, fasting blood sugar. So the data kind of gets cleaned in a way that we understand what the outcomes are. And the thing that we're trying to predict, heart disease, is a binary value. And it's basically going to be the Y in all of the following experiments. So we got kind of lucky with this data set. There wasn't any null values. There wasn't any crazy outliers. I didn't see anything that was impossible, which made it a little bit nicer to work with. And the first thing that we're going to do, we're going to normalize the data, and then we're going to go ahead and from sklearn do the linear model. And one of these cells didn't get ran. If that's not working. All right, let's just do this. There we go. So what we have here is a coefficient plot, and it's going to basically just say how much each of the factors contributes to the outcome on the linear model. And according to this, gender is the biggest contributor to predicting heart disease on our data set, followed by angina, thalassemia, and of course chest pain is probably a pretty good indicator for heart attacks and heart disease. From there we have our R2 score, and that basically kind of sets a benchmark for the mechanics of the experiment, just to see how we come up in the final value when we test our own algorithm. In addition to the linear regression, also from sklearn, we have a random forest classifier of decision trees. So we do the test train split. We make our model and train it with the training data, and come up with even more problems in code. You can't beat live recording. I wonder what cell I'm not running. Anyways, after the test train split, we go ahead and do our predictions for the... Oh yeah, basically we're just comparing the actual values with the predicted values, and we accumulate a sum. So for this one, out of 76, we got 55 correct, which makes the random forest about 72% accurate, which sets a benchmark. So from there we do a Shapley additive explanation, import the JavaScript explainer here to kind of see how it came up with that. And once again, it has gender as the biggest determination, and thalassemia is on the list of the top three. But it's also saying the cardiogram is in there, as opposed to, yeah, that wasn't even a very big contributor in the linear model. So it's coming up with kind of a similar model to the linear regression, but slightly different. So we have this SHAP analysis here, and it basically just shows how striated the values are on the data set. So, you know, chest pain, obviously people that have it are a lot more likely to have heart disease. Once again, gender, you can see being a male is hugely more indicating than being a female. So basically, as it says, this is the impact on the output. Some things are a little less deterministic, like cholesterol. You can have high or low cholesterol and still kind of get away with not having heart disease, and your max heart rate isn't quite such a big determination on that. So from here, we got pretty good benchmarks that we can test our own algorithm off of. So this is a function we made. It trains our model. It takes in the data set that we had and what we're trying to predict. We're going to take the positive. Any place where heart disease equals 1 means that that's positive for what we're trying to do. And we're going to take the mean of that value, and that goes into our model. And it's a brand new data set called Positive Compare. And we are going to do the same thing for any place that heart disease is negative and add that to a data set. Then we're going to do a Pearson correlation coefficient, which is going to be the weights. All of these get added to one data frame, which is our model. And as you can see here, out of all the positive heart disease cases, these are the means for every value. These are the means for negative values. And these are the weights overall for how much the X correlates with the Y, basically how linear it is, how much, generally speaking, the X's go up cause the Y to go up or down, and vice versa. So you could see from our model that gender is not as big of a contributor in the end. Chest pain still is, max heart rate is, angina, thalassemia is lower on the list. So definitely, with the simple prediction algorithm, we're kind of taking a different route to end up at the conclusion. But this is the output of what the model looks like and what we do. So here's the algorithm for predicting. For the elements in the data set, we're going to get the Y, which once again, when we input that, that's going to be heart disease. The individual element, that's just going to be one thing from the entire data set that we're trying to predict, and then the model that we generated up here. So we're going to take the sum of all these correlation coefficients and make that a value. I think in this it was like 3 or so. And we're going to have a threshold that is that total divided by 2. So everything gets made into absolute values. The positives turn into a list, the negatives turn into a list. And what we do is we're actually comparing if the value for every feature in that element from the data set, if it's closer to the negative value, then, well, if it's closer to the positive value, then the Pearson correlation gets appended to the total score. And if at the end of it, that crosses the threshold, which is half of it, it basically either predicts, it either says that it's a 1 or a 0 for true and false. So the output of this function has the actual value that we got, and then it has the predicted value. So what it looks like in action is this right here. We run the entire data set in. So for every element in the data frame, we do that prediction algorithm up here and try to predict heart disease after we've trained it off the entire model. And as you can see, for something that's not split up yet, it looks like we are about 83% accurate. So to then compare that to what we did earlier with the random forest, we're going to go ahead and do the same train test split. 20% is going to be the test size. 80% that's left over is going to train the model. So we run the train the model function to predict heart disease. And for every element that is in the test bracket, If our prediction matches the actual y value, count gets added. And then at the end of it, you get that output that we have up here. So we were 83% accurate on something that's not split. We're going to go ahead and do the test train split, and we're going to conduct this experiment 50 times on it, randomly selecting 80% of the data to train on and 20% to test on. And the result of that is here. So it looks like, 51 out of 61, 77% accurate, 85, 90s, 70s. Generally speaking, the simple prediction algorithm is performing a little bit better than the random forest. And here's a graph of that output. On the low side, we might be 70% accurate. On the high side, we're actually up above 90. So we're pretty happy with it. It's working quite well. For something that's just literally using means and Pearson correlation coefficients, it's actually outperforming sklearn's library. So, what else do we got here? That's the experiment and a little bit of the analysis, benchmarks, conclusions. Yes, conclusion. So the conclusion is we made a working algorithm for predicting heart disease, and we're very happy with that. But there's a few things. For one thing, we're only comparing individual elements and then just using the correlation coefficient. So like Shapley is going to look how things combine to create an outcome. So if you were to give this algorithm some data that doesn't have a high amount of correlation, it probably would not be performing better than a random forest or a decision tree, probably more similar to linear regression. Also, since we're doing the Pearson, its outliers are going to totally throw it off. So if the data has little anomalies in it, our algorithm is going to have big problems predicting good outcomes. We could probably change that up by doing a Spearman correlation or some, linear regression, but this is the simple prediction algorithm, so we literally went with the most simple formulas that we possibly could. It only takes 2 pieces of data to train this, and if they're not outliers, if they're middle values, it can be trained just on 1 positive and 1 negative outcome. It's super simple. It requires no computing power. You could see that I think we only had 303 elements on this data set. So, to find the mean of anything and then predict stuff, if you don't have data that's too anomalous and too squirrely, it actually should be pretty accurate. So in conclusion, I'm at least quite happy with the outcome, and probably wouldn't want to use it for absolutely everything, but it does work. So that is the results of our experiment.